Hello everyone, and welcome to this session of Asset Hub webinar, a series to get you up and running in the Polkadot ecosystem interacting with Asset Hub. In previous sessions, we talked about the reason for Asset Hub, how to open a channel to it, register your Parachain token or your Parachain asset, and also the asset conversion palette and the asset transfer API. In this session, we'll talk a little bit about XCM, which you've heard of before in the series, and how to configure a parachain to send and receive different assets to and from Asset Hub. So let's get started. In the screen, I have a little diagram showing a hierarchy of locations. One of the key concepts of XCM is the concept of a location to locate something in the world. Here we can see that different blockchain networks can be located, for example, Polkadot, Kusama, and Ethereum, all underneath an imaginary universal location, which would be like the root of this location tree. So locations define a hierarchy where you can go up the hierarchy, and there's only one way to go up, or you can go down the hierarchy in different ways. So under the universal location, we have, for example, Polkadot, Kusama, Ethereum, Bitcoin, and all the other, we call them global consensus systems. Just a fancy term for their own blockchain networks that are not interior to others, and we see that with, for example, parachains. They are blockchains, but they are inner to, for example, Polkadot. That's because a state change in one of them implies a state change in the other. So with this in mind, we can go on and talk about configurations. But we want to talk, I'll show you one more thing first. What we want to do, as we saw in one of the other sessions, we can open a channel with Asset Hub and then register our own Parachain token. So this is useful for anyone that wants to create a Parachain. Registering their asset on Asset Hub allows you to have access to many more parachains. That is, you have access to different dexes and different utilities that you might want your asset to be used for or traded for. And instead of having to create a channel with all of those parachains, you can just create a channel with Asset Hub, and then all of the parachains connected to Asset Hub, which are a lot, can have access to your token. What we want to do now is talk about the configuration aspect of that, and also not only how can we send our Parachain native token to Asset Hub, but also how can we get different assets from Asset Hub into our Parachain, so we can also use them for different things. With that out of the way, let's ask the question where to start. So, one of the best ways to start is to use a template. Here we can see a list of templates. These are all under the Polkadot SDK docs, which are Rust docs, which you can find under partytech.github.io/Polkadot SDK. Here we have a lot of documentation on all the topics we will be talking about and more. And one of the sections talks about these templates. Here we have 3 templates that are internal to the Polkadot SDK repository. They are the minimal template, the solo chain template, and the parachain template. We will be concerning ourselves with the parachain template in this session. The minimal is more for learning and testing, and the solo chain is better for not connecting to the Polkadot ecosystem, but rather having a standalone substrate-based chain or Polkadot SDK-based chain. And then there are other templates, not only inside the Polkadot SDK repository, for example, OpenZeppelin with the generic runtime template and EVM runtime template. And also Pop CLI is a nice CLI tool that also provides some templates when you run their CI commands to start your own parachain. This is also a good tool to start. Great, so let's say we grabbed the Parachain template. Now we want to know how to make it interact with Asset Hub. For resources on how to actually launch it, there's the very nice EduChain resource that was shared in one of the previous sessions. So this is the Parachain template repository. This is auto-generated from the Polkadot SDK repo. There's a folder there with the same name, and it just gets brought here, so it's always up to date with the latest and greatest. Here we can see there's a structure, a node, a runtime, and pallets. If you know about Frame, you know what those are. In the docs that I mentioned, there's a lot of resources about Frame if you want to know more. And then to get started, you can see that you just download the repository, build it, and then there's even a ZombieNet configuration to boot up a local network and test it. And then you can connect your network with Polkadot.js apps, another tool that was used in other sessions. So this is a good place to start. Now let's move into the XCM configuration. Take a look at what the vanilla XCM configuration for this parachain looks like. And let's see how we can change it to make it interact with Asset Hub. Here we are in an editor, a terminal, with the Parachain template open. This is the README that we just saw. And what we're interested in, you can see the structure of this repository is what the node, the runtime, and the pallets we saw. But inside the runtime, there are some interesting things. One is the lib file that has all the pallets, little modules of logic inside of our blockchain runtime, containing the business logic of our blockchain. Here we can see them if we look for runtime : runtime, or the outer one, frame support : runtime. So here we define all of the pallets of our runtime. For example, we have a balances pallet that defines the native token of the chain that we can do transfers with it, and we can lock it for different things. Then we have the pseudo pallet, which allows one account to have root privileges over the chain. This is a very good idea for the start of a blockchain network, and then after you get enough momentum going and different validators and decentralization, or in the case of a parachain, different collators, you can end a better governance system, different users. You can remove the pseudo key and then move on to a more decentralized or open governance system via, for example, runtime upgrades, which are something that Substrate or the Polkadot SDK provides. And then there are some more pallets. What we're mostly interested in is this configs folder. We have this mod.rs where the different pallets are configured. And there's this XCMConfig file where the XCM configuration is. So let's see what that has. Here we see a bunch of imports, and I'll probably zoom in a bit. There we go. Which we'll see what they are afterwards, if needed. We have this parameter types macro, which this block of code, what it does is basically give us access to these variables, which are declared in a funny way. but basically they are the relay location, which is the parent location. This goes back to the diagram that I showed earlier, where you can go up the hierarchy to reference other locations. Here we also see that locations can be relative, and we can describe the location of different things in the world relative to our location in the world, relative to us. So for all parachains in a network like Polkadot, Kusama, or some testnet that mimics them, will be location parent. For all, location parent will be the relay chain. So this is relay location. Then we have relay network, which is currently set to none, but this would be something like, for example, Polkadot Kusama or one of the testnets. So now we can go ahead and change it to, for example, Rococo, which is one of the testnets. This relay chain origin, we're not going to talk about it very much. And then we see this universal location. The universal location should be called absolute location. It's from the root that I showed, from the universal location. How can we go down the hierarchy into our chain, into our parachain? So this to be an absolute location, we talked about how locations can be relative. Location can be absolute. If we specify it's an interior location, it means it doesn't have parents. And if it starts with the global consensus junction, we call each path you can take down the location hierarchy, we call that a junction. So if it doesn't have any parents and it starts with the global consensus junction, it's probably an absolute location. Depends on the context of how you're using your locations. But in this case, this universal location variable is just the absolute location of our chain, and we can do what it says here, that for real deployment we should change this. So let's change it to global parachain, not global parachain, but rather global consensus. And then we want to grab that network that we defined. This get syntax is how we access these variables defined within parameter types. So just do global consensus relay chain network get, and because this is an option, we need to unwrap it. This will just fail to compile if this doesn't exist. I mean, we know it exists, so it doesn't matter anyway. And then after the global consensus, we see the parachain. This parachain junction already holds the parachain ID. So each parachain under Polkadot, Kusama, or the testnets, we have a parachain ID assigned to it. And for example, asset hubs, asset ID, parachain ID is 1000. And then we just need to finish this up and do another into. Good, that's one of the first things you might want to do when you grab a Parachain template. Let's keep and see what we have here. We have this location to account ID type. You'll see with XCM configuration that it's a lot of types that then all get sort of amalgamated together in one huge XCM configuration type. This type, location to account ID, is basically a converter from those locations we talked about before. So parent, parachain, all those things, into account IDs. So actual accounts, local accounts, they can hold funds, transfer, so on. So here we have one for converting the parent location, one for converting the sibling, which would be parents 1, and then parachain down, the sibling parachain. And then this account ID 32 aliases, which grabs an account ID 32 junction, which we have one of those, and just directly converts it into an account ID. They hold the same data. In the future, keep in mind that this Parachain template might look different because some configurations might be changed or some new features might be added. Then we have the asset transactor. This is a very important configuration item, which is how does XCM deal with the assets on this chain. So here we can define very interesting things. For example, here we define how we want to deal with assets coming in from the outside of our chain. Where do we put them? How do we recognize them? So that's something we'll be talking about because we want to know how to send and receive different assets to and from Asset Hub and our chain. So for now, here we have a fungible adapter, which there's this pattern you'll see with the XCM configuration. We provide these adapters that you just need to configure with generics, so these inner types, and then it's done. And we have adapters for very common scenarios, use cases. Here, this fungible adapter is a transactor that deals with one particular asset. So this is usually used, for example, for the native asset of your chain. And all of these types that you see being thrown around, they are part of this huge XCM builder import. XCM builder is a crate where we expose a lot of these helper types. Let's keep on going. So this dispatch origin, we won't bother ourselves much with it. It can basically remain unchanged. We'll need to change the transactor, but we can leave this unchanged. It's how do we convert an XCM, an incoming XCM, so a location, not into an account, but rather into an origin. Origins are more flexible than accounts, and they can be, but they can show different permissions. Like for example, root is not an account, but it's an origin, and we can define different origins and play around with different permissions for different operations, for example. Here you have some new variables, so parameter types block. This is a very much just a testing value and should be changed when going live. This is the unit weight cost, which says that one XCM operation, which is one XCM instruction, we've seen on this webinar that an XCM is composed of multiple instructions. This shows that one instruction is 1 and 9 zeros of weight. Almost certainly a conservative estimate. And we can see that it's 1 and 9 zeros of the first part of the weight, and then 69 times 1024 for the second part of the weight. This is because weight is two-dimensional, and it calculates or it measures space and time used by this computation. This should be changed by using benchmarks, which there's a frame benchmarking framework. There's more about it on the docs. But before going live, each instruction should be benchmarked to see exactly how much it costs, and that will translate into actually fee cost for users. I have these two values which can stay like this. There are max instructions of 100. It could be even smaller, bigger, depending on what happens usually. And then the max assets into holding, which 64 is more than enough for usual cases, at least. We got this type called parent or parents executive plurality. It is just an empty, like a unit type, doesn't have any data associated with it, but it has this functionality associated with it, which is part of this contains location trait. This contains location, what it provides is just sort of makes this a filter for locations. So check if a location is a parent or a parent's executive plurality. Here you can see that it matches a location that has one parent and no junctions, or one parent, so parents 1, and one junction called plurality with the body ID of executive. This might mean something like, for example, governance. So the decision of the whole network might be this executive plurality. Good. These filters are usually helpful for the next thing we're going to talk about, which is the barrier. The barrier is a sort of firewall for XCMs. It's where we can define what messages we're gonna let through and what messages we're gonna block. So here you see a lot of types: trailing set topic as ID, deny then try, deny reserved transfer, take with credit. We're not gonna talk about all of them. It would be very boring if we did, and we would be getting away from the most important ones and the things we want to talk about. But they are interesting to know what they do before or as you grab this Parachain template and start playing around with it. You will, and playing around with XCM specifically, you will learn what these do and look them up and see what they do. Maybe remove them, change them to your liking. These two might be the most important ones, alongside this computed origin, which allows regular users to send XCMs. These two might be one of the most important ones. This first one blocks all messages that do not intend to pay for fees. We have an XCM instruction called by execution. In the future, an instruction called pay fees. They deal with fee payment, and users have to include them in their XCMs. Users or applications, front-end applications, the apps. If they don't, this barrier will block them immediately, will drop them. However, if they do, then this one allows everything, and here you see we allow messages from everything. So every other parachain or the relay chain that we have a channel to, we could constrain this further if we wanted to. And then this one is called allow explicit unpaid execution from. So here we allow messages that do not pay for fees. They have to explicitly add an instruction called unpaid execution. But we can also further constrain this type. Here we see, of course, we don't want everyone to not pay for fees. So this is usually just some group of locations that might not need to pay for fees. So here parent or parent's executive plurality doesn't need to pay for fees. This could be anything really. For example, the relay chain root, right? Not a user on the relay chain, but the relay chain root doesn't need to pay for fees, for example. That can be very useful. Or different parachains or different pluralities, different bodies, even different accounts, if you find it useful, don't need to pay for fees when they send an XCM here. Great. So now that we talk about the barrier, let's talk about the rest of the things. Now let's talk about the XCMConfig amalgamation. So this type has a lot of associated types, as we can see. So that's one of the advantages of using a template. The two, or maybe we talked about the asset transactor, that's very important. So maybe the three most important ones that we care about for this session are the asset transactor, is reserve, and is teleporter. Don't worry, most of this you don't need to care about too much or change too much. We have safe and good defaults with this template. So, and here we can see we set the universal location we talked about, we set the barrier, we set the transactor, and we're going to set these two to interact with Asset Hub. Other than that, we have the XCM router, which sends messages to different, is the one in charge of sending messages to different places. Here we have this parent as UMB, which will send messages to the relay chain, and then this XCMPQ, which will send messages to other parachains. And then this Pallet XCMConfig is not part of the XCM configuration, but it's a configuration for a pallet. It's the XCM pallet, the pallet that is an interface between the frame subsystem and the XCM subsystem. This pallet provides transactions that users can submit to interact with XCM, so to send messages or execute them locally, and so on. Good. Now that that walkthrough is out of the way, let's change this configuration a bit. The first thing we want to change is this isTeleporter field. So in order for us to register our asset on Asset Hub, we saw that in a previous session, we can open a channel and then send a message where we call a particular function registering our asset. Once the asset is registered, we can teleport our native asset to Asset Hub, and Asset Hub can teleport it back to us. So in this sense, teleporting is a very simple transfer mechanism where we trust the other party. We burn every time we want to send something, and they mint it on their side. We can use this type of transfer with Asset Hub because if we trust Polkadot, which we do if we're a parachain, we run it on top of it. We also trust Asset Hub by extension because it's a system parachain. So that's why we can teleport. Usually you don't teleport directly to other parachains, since parachains that are not part of the system are sovereign and you don't necessarily trust them with your asset. If you teleport them, there's no way to distinguish between one asset from one chain and the other. So the other chain might mint 1 million of your token, or other bad things can happen. But we can do it with Asset Hub, and it's the way to go for registering assets and then sending assets to and from Asset Hub. So we will want some variables for this. So let's create a parameter types block. Here we can have this native, we can define the native token, which is an asset ID. It's going to be asset ID, and then location here. So the native token version is here. Then we want to define native token filter, which is an asset filter. Filters, the assets usually need to be specified how much of the asset, and asset filters allow you to say, well, all of this asset. So here we would say a wild, so like a wild card, all of, wild fungible. This is to specify the fungibility of our asset. XCM allows for both NFTs and the fungible assets. And then our ID, I think it's called ID, the compiler will tell us, will be this native token, and remember get. Here I have another tab with the project, which I can use to build this Polkadot, nope, not that one, this Parachain Template node. And for this purposes, we don't need it to be release. We don't even Needed to be the node, it could just be the runtime. There we go. And we don't even need it to be build. We can just do check. So cargo check will be faster. Oh, in this case, since I have already built it before, check is not gonna be, check is gonna start from scratch. Check doesn't need to build the binary. It just checks types and that everything is correct. So we'll let that run. Meanwhile, we're gonna define this asset hub location, just a location, and we'll do location new. Now from our parachain, how do we get to asset hub? We do parents 1 and then a list of junctions, but that junction is just parachain 1000. And instead of doing 1000 there, we can go up top and maybe add a constant somewhere, which is asset hub ID, just a number, and we put that as 1000. And then we go back to our asset hub location and we can use our new constant. It's just a good practice to always name things just in case. And then we can do what we wanted, which is to define this asset hub trusted teleporter. This is a tuple of asset filter and location, which defines what location we trust as a teleporter for what assets. So here we can just put our native token filter in the first part and asset hub as the second part. Now the check passed, let's run check again, much faster the second time because we didn't change all of the underlying dependencies, only this file. While it checks, I'll just go back. Now once we have this, we can create a type that uses this tuple that we defined. So let's go type, trusted teleporter. This could be trusted teleporters, but we only have one. Then from XCM builder, we have this type called case, which transforms this tuple. So that's why we took all the work of putting this in a tuple. Transforms this tuple into what we want. Now, trusted teleporter. We can just plug it in. See the check run, and now we should run it again for this trusted teleporter thing. Here, we now trust the asset hub with the asset whose location is here. So we can send our asset to asset hub. However, when asset hub sends it back, how do we recognize that it's ours? I mean, it will have the same location, has to, that way we can recognize it. But the asset transactor is the one that is in charge of grabbing the location and actually transforming it into something that goes into some pallet, which is the underlying implementation of the asset. So if we go back to our transactor, asset transactor, we see that this fungible adapter will use this pallet balances, which this name comes from runtime source lib, where we saw we defined all our pallets. So we search for runtime, and we see that balances is the name that we assign here to pallet balances. So any we'll see that we will use this transactor when the asset matches this location, which is this one. It's concrete, it's just like a helper type that adjusts all the underlying types. Relay location. So whenever this matches, we'll use this pallet. Now we see a problem here. This means that we can send our, this means that we don't have any transactor that deals with our native token, we're only dealing with the relay chain token. So something that would be better would be change this to a here something, and we can define that here, for example. And that would mean that we do deal with our native token as if it was different to other different tokens. Keep in mind that if we are launching a parachain and we don't want to have a parachain token, we can actually leave this as the relay location, start with 0 balance, and then accept reserve asset transfers from Asset Hub. We cannot accept teleports, the simpler mechanism where one part burns and the other part mints, because we cannot be trusted with the relay chain token, which could be DOT, or KSM, or ROC in Rococo the testing, or PAS in Paseo, the future testnet, which is already live, but is the one that Rococo is being deprecated in favor of Paseo. We cannot be trusted with the relay chain token, but we can still receive some of it via this reserve asset transfer mechanism. The reserve transfer asset mechanism is one where one chain is the reserve. They are the ones that control the token, and they can send the sum of that token just by depositing it on a local account on their side that represents how many tokens our parachain was given, and then they send an XCM to our chain saying, hey, your account on my chain has X amount of tokens. You can go ahead and mint derivative tokens, the same amount of derivative tokens. And we call that account that represents you on a different chain, we call that the sovereign account of your chain. So once you mint those derivatives, even if you went haywire and minted 1,000,000 derivatives, the real asset stays in the reserve. So that's how we could get relay chain token, so ROC, KSM, DOT. But that's also how we can get other assets native to Asset Hub, or not necessarily native to Asset Hub, but other assets from different parachains that have gone through this same process of registering on Asset Hub. Because once you teleport your asset to Asset Hub, once you have this relationship of teleporting, then the other part, so Asset Hub, can also act as a reserve for your asset. This is the way in which we open up our asset to the rest of the ecosystem once we register it on Asset Hub. Good. Now, let's actually keep this as here location and know that this is all we need to be able to handle our assets. We have one more thing we need for teleports, which is this thing down here. It says we don't track any teleports. We actually do, so let's just remove this. And what is this? This is a checking account. So checking accounts, and it's been a while since I last checked. Speaking of checking, so I'll run the check command again. The checking account is sort of this account where whenever we burn tokens, instead of burning them, we send them to this account. I mean, it depends on whether the asset we are teleporting is us or not. Like whenever you teleport to another parachain, the asset is considered to be the same in one chain or the other. Like it's not like any of them is the owner. They're kind of both the owners. That's why both of them can act as reserves. However, for bookkeeping purposes, for due diligence, so for counting the total issuance, it's better to have one of the chains take care of counting the total issuance. Because of this, one of the chains will define a checking account, and whenever they teleport assets away from the chain, they will add to that account, and whenever the assets come back, they will subtract from that account, just to keep the total issuance in one place. In that case, it counts how many assets have gone away. Okay, so we need some checking account here. See a check passed. Let's do checking account. This would be an account, and we actually have this helper called check. I think it's called check account. I'm not sure though. This is a helper we have in the XCM palette. So if you go back to runtime source lib and we go to Polkadot XCM, we see it's the Pallet XCM. We give it this name. And then if we check it, this is probably not the name. Sometimes with this thing it's very hard to know like how many different types and functions exist to use. So if we check it, we see it actually works. So then this is the name. Good for us. And now we can put it here, checking account. We track telephones. Let's check it again. But one way, if that was not the name, there you go. We got an error, which is saying something about the checking account. It says it has to be something like an account ID 32 and mint location. Yes, so now this is an interesting thing, or an interesting question. How do we know? So we can actually go to the source of this fungible adapter and see what we need to pass it in. So apparently it's not just an account. So if we go, I have in another tab, I have Polkadot SDK open. So if you go to Polkadot SDK, the repository, you'll see most of the code that you're going to interact with. So here we can search for the fungible adapter. I know this one came from XCM Builder, so you can search for it, and here it is, fungible adapter. We can see these are all the same generics that we were dealing with. And we see here this last checking account. The checking account is an option of a tuple with an account and a mint location. So that means we not only need this. So let's see, maybe we need to do checking and then account ID and then this mint location. We can have this checking account. And then what's this mint location? We can very well look for it. So I'm just doing Control F globally. And most of these types are in XCM Builder. So if you go to XCM Builder, you'll see it. And we see this mint location is defined in Fungibles adapter. There you go. The only thing it is, it's either local or non-local. So this is what I was saying about either being the one that is allowed to mint the asset or not allowed to mint the asset, so that we can track teleports in and out easier. So here, let's say it's the local, and we will only mint locally. So then we can just say local, and this mint location, we'll need to import it from XCM Builder for sure. Let's just add it here, mint location, and then we're back. And now, instead of checking account, we want this checking tuple we just created. Now let's see if that works. It takes a while. You see that checking takes a while. There you go, it works. So the only thing we did is go to the Polkadot SDK, which you can have locally, or you can use the repository on GitHub. And we search for all these things inside XCM Builder because we know they're XCM configuration types, so most likely they're in XCM Builder. Another thing you could have done is to go to definition if you're using an LSP, language server provider. Great. So with this, we are done with the teleporting aspect. Now let's look into reserve asset transfers. So we talked about teleports, which is how we can move our native token from our chain to Asset Hub and from Asset Hub back. Now we'll talk about reserve asset transfer, which is how we can get other assets from Asset Hub into our chain. These other assets might be the relay chain asset, might be assets that created in Asset Hub like meme coins, or different parachain tokens that have registered their asset with Asset Hub. In Asset Hub, let's go. So now, here in this is reserve, we used to have this native asset helper type, which comes directly from XCM Builder. This means that we will trust chains as a reserve for their own native asset. This is sensible. It's a good configuration to have, but it won't work with Asset Hub because it will try to find like an Asset Hub native asset when really the Asset Hub native asset is the relay chain asset, and it won't figure that out for us. Also, there are multiple assets inside of Asset Hub, like meme coins, and also foreign assets, which are these assets from other parachains that will register there. So what we want to do is create a new type called assets from, where the idea is we accept Asset Hub as a reserve, we trust it as a reserve for any asset, as long as it's from Asset Hub. And it doesn't matter what we get, we can deal with it later on the transactor stage. Now let's look into creating this type. This is reserve. We'll implement a particular trait. Let's create this struct will be assets from, and we'll take some value. This T will be our location, which here is Asset Hub. We know it's location. And if we put a generic and don't put anything in the type, we'll get a compiler warning, or I think even an error. So what we need to do is add this phantom data type. This is sort of a hack to tell the compiler, hey, we actually will be using this type, don't worry about it. But it's not like we're using the data from the type, we're using some behaviors associated with type. And this phantom data comes from core marker. which is like the standard library but smaller. Great, and now we need to implement a trait phrase reserve. If you want to know what trait, we can go to the Polkadot SDK. I mean, we can always go to definition, but if you go to Polkadot SDK, we'll find this under XCM executor config. This file defines all the configuration items. You can see the traits for all of them. So for example here, the trait is called contains pair, and it's a pair between asset and location, which we trust the location for the reserve as a reserve of that asset. So let's do that. Let's implement contains pair asset location for our assets from. And we have to specify this t, and here is where we can actually bound our t with some behavior, some functionality, and the functionality we want is get location. This get is the thing that lets us get the variables from here by doing this colon get. So this is how you use these things in your own types. So here, I guess this type contains pair. We can always like look it up. We copy, search for it, see that it's apparent in frame support the traits. It's in members. It's here. So it has a function called contains. So let's do a function. Apparently it takes an A and a B, which we know the types already, and returns a bool. So let's grab this t, sort of a prefix, and we don't really care about the asset as long as it comes from asset hub. So we just need to return whether or not the prefix is equal to this location we have here, or better yet, the location that we got this from is our prefix. We can call it prefix, we can call it location really, but we already use location. And this ampersand is just because this location type is of type ampersand location, so a borrow of location, so we need to add this ampersand, and that's it. So now this type, which we can already start checking, this type will accept asset hub as a reserve for anything, because it doesn't look into the assets. We can see it here. And that's good. I mean, it's not a bad configuration. You can certainly be constrained even further. One of the constraints we can do is say, okay, we can say it acts as a reserve for everything except our own asset. Because if it's a teleporter for our asset, then it shouldn't also be, it can't also be a reserve for. So let's call these assets from except, and let's have our assets. So I guess here location, or I guess we can use this native token type that we have here, which is an asset ID. And then we can rename this guy, yeah, we need to import some stuff. So let's go back. Let's actually check this check before. It's always a good idea to write some code, at least when working with Rust. It's a good idea to write some code, compile it, see if it works, and then always be in a state of it being compiling. So we see only two errors. One is that we don't know where this contains pair comes from, and the other one is we don't know where this get comes from. We see it's very simple. One comes from SPA core, for example, and the other one from frame support traits. So let's get it. We have frame support traits already. There we go. And then we don't have SPA core, but apparently we have it in our dependencies because we saw it here. Let's see if that fixes it. Here we are again. I don't want to do anything before. There we go. Now we're in a good state. Let's keep on going. So what I was saying is that we can get all assets except our native token. For that, we can rename our type and then maybe add an E type. Here we need to put a tuple, and then we get T is a get location, and we get to E is a get asset ID. So the same type is here, wrapped in a get. So now we pass in our two generics here, and now we do care about the asset. We can do something like asset ID to exclude, and then we want to only return true if this is coming from asset hub and the asset.id is different from asset ID to exclude, and then that will be a much better type. Let's see if this compiles. We didn't change the name, so we change the name here. That was very fast. Once this is done, we will accept asset hub as a reserve, which means we can start getting assets from it, different assets other than our native token. But even if we accept them, like even if we trust asset hub, we still need to do something with them. Where do they go when we actually recognize them? We don't have any code for that right now, but we use a transactor. But we can't reuse the same transactor we have. We need a new one. So let's go ahead and create a new one. So in order to be able to get these assets and put them somewhere, we need a new transactor. But we don't have anywhere to put them right now. We cannot put them in balances, and we need to put them in a pallet. If we go to runtime lib and we go to runtime, we see we got system timestamp balances, and we don't really have anything that could look like it could support this. So we need to add a pallet. So let's do runtime pallet index. Let's do 40 just because it doesn't collide with anything. And let's call this foreign assets. Similar to asset hubs, foreign assets, but this will be just to hold assets that come from asset hub. So here we do pallet assets, and we need to add some configuration for this pallet. We also need to add this to our dependencies. So if we go to runtime cargo.toml where we have our dependencies, we'll see the dependency for pallet balances. We can add one for pallet assets. Apparently we inherit them all from our workspace. The workspace dependencies are in the root cargo.toml. So here if we go to pallet balances, we'll see the actual version we're using. We can add a pallet assets, which I checked in crates.io, and the last version is this one. There we go. We just copy what's in the rest. With that, don't check quite yet, because there will be a lot of errors because we don't set a configuration for this yet. So we want to go to runtime configs mod Then we can go to Pallet balances. And next to this, we can have this configuration. So I copied a configuration that I have only to make this faster to type. It's basically the only relevant things are this asset ID and asset ID parameter. This will, for example, on asset hub, there's one instance of this pallet in which the asset ID is a number. And anyone can just go in, create an asset, and it will have ID 1, 2, 3, and so on. So I don't think it's auto increasing, but you can create any asset with any ID you want. Here, because we'll be using this palette only to hold assets that come from Asset Hub that are different from our native token, we could just, instead of having to map the location to a number, we could just use the location itself as an asset ID. So that's the most important part. And then we have this create origin, which is who can create. We don't have this type, so we will be figuring out a new one. And who can force is root. And then all of these constants, we don't have them yet. So let's just define them. So for example, we have asset deposit, which looks like a U32. Yep. And we can just, or actually this should be a balance. If you check, we have a balance type. This is the type we're using for balances. So we have that, we have the, and all the rest pretty much without this freezer. So what we can do is just change this to pub. I'm gonna make sure these are balances, and then we can change them all to 1 because we don't really care about them right now. There are different configurations that you can look into on your own and see what they do. Great, and then this derive impl will fill in a lot of configurations with defaults. This is very useful when you are just testing or starting out. If we check right now, this should pass. Well, other than some import that we're missing this location. We know location comes from XCM. So for example, here we have XCM latest. Let's just get the location from here. There we go. And this should already work. Yeah, and create origin. We need to specify something that works. So that's missing right now. But we will fix it. For now, this works if we, other than this, if we were to remove this, then more configuration items would appear and we would have to specify them. How can I know which things are configurable? You would go to the source. So here I'm in Polkadot SDK, and I can, all our pallets are under frame, so substrate frame, and in this case it's assets. So I go to the lib, and we'll have something under pallet ::config, and this is the config. So you can see the balance type, you can see asset ID parameter, currency, create origin, all of that. And given that we're here, and we see some information about the defaults. And now that we're here, we can see this ensure origin with arg. This is the trait that create origin has to implement. And we can see this success self account ID, which means that if the origin permission check, like if the origin check succeeds, it will return an account ID. In this case, to be the owner of the asset. So let's see what we can create here. We want root to be able to define assets, to create assets that we know have a correspondence on Asset Hub, and we don't even want to mint them. We just want to create them so they can be deposited from reserve asset transfers from Asset Hub. So we want some sort of ensured root. However, this won't work if we try it because it doesn't return an account. It expected an account and it found nothing. So we need to create a type that fixes this. Let's create ensure asset owner, for example. And then we implement this trait ensure origin with arg. And this has a few generics, we'll see them now. So here we need to pass in the origin and the location in this case. And this you can see again, if we grab this asset origin again in Polkadot SDK and we search for it, and we see that it's in frame support traits. So we go to frame support traits. We see it comes from this patch, and here we are. So we see it takes another origin, which in this case is the runtime origin. You can read more about it in the docs under aggregated types or runtime types. And then some argument, which in this case we know it's allocation. If not, the compiler will tell us. And then we have a success type and this function, which is the magic. This will check the origin is correct and then return the success value, which in our case is an account. And then we have this try origin, which actually is the function that is being called here. So wait, this is what we need to implement. It takes an origin and an argument. So let's try it out. Let's first use the account ID as a success type, and then let's implement try origin. This returns a result of our success type or the outer origin. We get our origin and their argument. Here we won't use our argument. The argument is for maybe different asset IDs can be created by different origins. So because our asset ID is location, that's why we're putting location here. But here what we want to do is actually ensure root this will return the error, and we map it to val origin, just like here, so that the error aligns. Oh, actually we don't map it to that, we need to map it to an outer origin, so we can map it to runtime origin none. And then this can happen, and then we can return an account. What account can we return? Well, we can have some asset owner, Pallet ID. This is a pattern that is used in, for example, the treasury and other pallets. We define some Pallet ID. They're named like this. That's why we are using this. I think there's a limit to how many bytes you can put here. And now this pallet ID has the property that we can actually turn it into an account. And now we have an account that is not controlled by anyone, any user, just by the runtime itself. And we can use it to be the owner of these assets that we actually decide via root, so via governance or via sudo key at the start. We're also going to use the sudo. So now we will see a lot of errors regarding imports, which will fix, for example, ensure origin with arg comes from frame support traits. So here, there we go. And then ensure root comes from frame system, the function, not the type. Let's see if it works. We still have ensure root. Yeah, and we want our new ensure asset owner, which doesn't even take account ID because it's very custom to our runtime. The argument should be an ampersand. And then this trait, we need to bring it into scope. And now that should be enough. With that, we can now launch a chain and root. So at the start, it will be the sudo key. In the future, it might be some governance system. Can create assets that are like, there's no asset, just the name. And then we can bring them in via Asset Hub. In order to bring them in, this is where the new converter comes in, new transactor comes in. So we need a transactor called, for example, foreign fungibles transactor, because it will be dealing with multiple assets, and we can use fungibles adapter. This fungibles adapter comes from XCM builder, fungibles adapter, and it takes a couple of things, very similar to fungible adapter. So the first thing it takes is the pallet, which we already defined as foreign assets. This we can get from here. This just takes it from the crate itself. Then we need some sort of matcher, which we'll fill out later. Then it's the same things as the one above, so location converter, which is actually to account ID. Then it's the actual account ID. And here we don't want to do checking because we don't want to do teleports. So we need to do no checking, and we actually need this checking account. We need to input some account here. Not necessarily this one, but some account. And this no checking, I think it comes from XCM builder, most likely. And again, we need it because of trait bounds. So what do we put here? Here we want something that matches on any location. Oh, well, not on any location. We could actually match on any location and put it where it needs to be. I was thinking it could match on anything except our local asset, but it could match absolutely everything because we already filter our local asset in the isReserve config item. So what we can do is have some foreign assets matcher. And don't be afraid of creating your own types for this. You can always check what traits you need to implement on the source, or the compiler will tell you. So let's do foreign assets matcher. This is struct. And we want to implement, well, actually, instead of implementing a trait, we have a helper for this. It's called matched converted concrete ID. And what it does is basically lets you very easily convert one ID to another and match it just by configuring this instead of implementing the trait yourself. So it takes out the asset ID first, location, then the balance trait. Then we can tell it to match everything. And then we need two things. We try and be weird at first, but it's because this helper type is very generic. We have how to convert from location to asset ID. So this type is meant for locations. And we need to know how to convert that into this. But because they're the same, we can use this type called just try, which will figure it out. And then we need to know how to convert from U128, which is the balance type for XCM, into this actual balance type. Because they're the same, we can just do that, just try again. And this will work. What the only thing we need now is to import other things. We already know by now, we just need to copy this, go to XCM Builder, it all comes from there anyway. And then we need the just try, just try doesn't come from here. It comes from XCM executor traits just try. Then balances. Fix of balance. We need this. Yeah. We already added it. Yeah. So let's check again. Oh, there we go. We can't find type balance in the scope. So we need it. So we can just get it from here. We get it from our runtime itself. And once this is done, we have a transactor that will receive. Yeah, there we go. We're not using them yet. It's a good point. So the way we use them is we copy them. We go to our asset transactor here, and we can actually put a tuple. So this transactor will match our native token. And if the asset that comes in is not the native token, then this one will not match, and it will go to the next one, and it will match this one. And then this one will just put it on our foreign assets palette. If we created an asset beforehand, so we can decide which assets we accept or not, and it will put it there, and it will be on the foreign assets palette. And it will accept it because we trust Asset Hub for anything except our native token. So then when you launch this chain, open a channel with Asset Hub, register your asset on Asset Hub, you will be able to teleport your asset from your Parachain to Asset Hub, bring it back, and you will be able, because of this and Transactor, you will be able to get, for example, if you're in Polkadot, you will be able to get dot on your chain, you will be able to get USDT, USDC on your chain, and any other parachain asset that has registered on Asset Hub, like for example Glimmer, HDX, and more. So with this, you have access to all of the ecosystem, all of the Polkadot ecosystem, just by connecting to Asset Hub. And with that, we are done with this session of the Asset Hub webinar. We learned a little bit about, we reviewed a little bit about XCM. We did a walkthrough of the XCM configuration of the Parachain template. We talked about how to teleport assets from your Parachain to Asset Hub, how to reserve transfer different assets from Asset Hub to your Parachain and back. And yeah, hope this was useful, and tune in to the next session of the webinar.